Okay. Welcome to this GATE online session. I am S.NIRMAL, Assistant Professor working in AIDS department. I am working in S.A.E. Engineering College. Today we have to see about the bias-variance trade-off. So it is an important topic coming under the artificial intelligence, and also it is already it's matching with our AI, ML, and also with the AI DS. So let us see the introduction of the AI. So in the bias variance trade-off, basically the bias variance trade-off is a core concept in a machine learning. Also it is coming under in the artificial intelligence also. So the main underlying principles is it describes a relationship between a model's complexity and its ability to generalize unseen data. So in the internet there will be lot of data which we can't able to see the data in with our eye. But when you go inside the server components, the data will be very heavy, and those data cannot be seen. So bias variance, this core concept in a machine learning that describes the relationship between the model's complexity. So how complex it is, there will be so many models, so that so many models will be there. So various types of models will have various complexity. So we have to analyze the types of complexity. Second point, it highlights a challenge of finding a model that is both on accurate training data, that is low bias, and also the variations in the low variance. So there will be different types of training data. We have to find the model which is suitable for that. Now come to the simpler terms. What is meant by bias? What is meant by variance? So in simpler terms, bias refers to the error. So that is the first concept. It is representing the error, only error, which causes the how this error causing the bias variance. Error introduced by approximating a real world problem which may be too complex. With a simplified model, high bias can lead to underfitting, where the model is too simple to capture and the underlying patterns in the data. So actually the real problem is it will capture the underlying patterns in the data. That is the bias. That is in the bias variance trade-off. The first word is bias. It is also known as the difference between the prediction of the values by machine learning model. So the prediction will be varying. So being high in the biasing gives a large error in training data as well as testing data. It is recommended that an algorithm should always be low biased to avoid the problem of underfitting. By high bias, the data predicted is in the straight line format. So if you see the graph, it will be, the line will be straight. So that is the concept coming here. Such fitting is known as the underfitting. So these types of line you will be calling it as underfitting. So this happens when the hypothesis is too simple or linear in nature. So when the hypothesis, if the hypothesis is very too simple, it will happen. Now come to the various. So bias refer to error. Now we have to see what is meant by variance. So when bias refers to error, this variance refers to model sensitivity. So to sensitivity to fluctuations. So in the training data, high variance can lead to overfitting, where the model learns the training data too well, including noise, and performs poorly on new and unseen data. So the variance refers to the model sensitivity to fluctuations. That is the one of the main important short reference to the variance. So whenever the word comes bias and variance trade-off, you have to keep remember that bias refers to error and variance refers to the model sensitivity. So with these two terms, which refers to the error and sensitivity, and it will capture the error with the unseen data. That is what they say, it as unseen data. It performs poorly on new and unseen data. In simpler terms, so now we've seen the bias variance. Now we have to see what is meant by trade-off. So trade-off arises because models with high complexity, low bias. When high complexity comes, we have to understand that the high complexity refers to low bias. Tends to have the high variance, and models with low complexity, high bias, that is the low complexity goes to high bias, whereas the high complexity goes to the low bias. That is opposite terms. Tends to the high variance, and models with low complexity, high bias tends to have low variance. So when this types of combination occurs, it will show that it is a low variance. Now come to the second category. If the algorithm is too simple, that is hypothesis with linear equation, then it may be on high and low variance condition, and thus it's error. You have to say that it is a error prone. So when this happens, you have to understand that it is a error prone. If algorithms fit too complex hypothesis with high degree of equation, then it may be on high variance and low bias. So in the last point, you have to note that in the later condition, the new entries will not perform well. So the new data will not perform well. That is the concept. Now you can see this in the picture representation. Now see what is how the picture and what is the definition. So bias is the error introduced on when an overly simple model is used to capture relatively complex relationship in data. So when complex relationship occurs, bias is the word we have to mention. High bias high bias leads to missing the relevant patterns and relationships in data and hence to underfitting. So there are two words, overfitting is there, underfitting is there. Overfits comes here, that is under variance, but underfitting comes under the bias. High bias leads to missing the relevant patterns and relationship in data and hence to underfitting. Now when it comes to variance is the error introduced when an overly complex model is used for the modeling. So you can see the graph here. So that is the x-axis, this is y-axis, you know that, and there is a line coming in between. This you will call it as optimal mode complexity. This line you have to mention it as optimal mode complexity. And this line, this black color line, you have to mention that it is a total error. And this red color line, you have to mention it as variance. So the graph should be drawn in such manner. And this mild line, that is the edges should be in both sides. We have to mention the arrows. This you are saying it as bias square. So the bias, this is the thing that you have to understand that it is a error. Okay, this is called total error and this is called variance, because variance is the error introduced when an overly complex model is used for modeling. Whenever you start modeling, if you use the overly complex model, it occurs the variance. So error on the x-axis and model complexity is on the y-axis. So this is the graph you have to draw when bias and variance trade-off comes for the question. So now understand, according to the graph, we have to understand some few terms. The bias variance trade-off is a fundamental concept in machine learning that underscores the delicate balance between a model's complexity and complexity. Model simplicity and complexity. Understanding this trade-off is crucial for optimizing machine learning algorithms for better predictive accuracy. So whenever better and predictive accuracy is needed, this bias trade-off is a best concept to come across. What principles underlines the variance trade-off in machine learning? So inside the machine learning, you have to understand what is the principle behind the bias variance trade-off. So the bias variance trade-off addresses the balance between two sources of error. So two types of error will be there. You have to understand the two sources first that affects the performance of the machine learning algorithms. That two source, which source is affecting the machine learning algorithm? This should be addressed. Next one is bias, that is error. Error due to overly simplistic assumptions in the machine learning algorithm. So if you take any one algorithm, if overly simplistic assumptions is there will be causing some error. And at last, the variance error due to the excessive sensitivity to small fluctuation. There will be a small fluctuation if you arise the query. Such queries will cause the variance error. That is the simpler terms in terms of variance. Now how this is working, that is high bias, high variance, optimal balance, these are the terms coming under, and underfitting, overfitting, just right. These three terms are coming under this bias variance trade-off. Now if you see this, how it works, how high bias and underfitting, you have to take a simple model. For example, you can say that linear regression. It may not be flexible enough to capture the true relationship between the input and output variables. So there will be some flexibility for simple models, but here there is no flexibility. That is what they are saying, it may not be flexible. So when there is no flexibility, you have to understand this point. This leads to systematic error, that is bias, where the model consistently misses the mark. So when there is a linear regression example, if there is no flexibility, you can face the error. That is one point. Now come to second point, high variance, that is you have to call it as overfitting. So in overfitting case, complex models, that is high degree of polynomial regression and deep neural network. This is the example, that is one is polynomial regression and another one is deep neural networks. So deep learning is there. They are saying it has deep neural networks, can perfectly fit the training data including noise. So here audio data also available. This means they are highly sensitive to a specific training set and will likely perform poorly on new data. So when new data is inserted into the machine learning algorithm, this will perform very poor, that is in the high variance, that is overfitting. And next one, optimal balance, that is you can say that it is just right, that is balanced level. Either high bias it will go for underfitting, and if you take the category of high variance, it is overfitting. Now if you come to the optimal balance, it is fitting the perfect line. So the goal is to find the model with a balance between bias and variance. So there is a problem between bias and variance. Here there is one solution, that is optimal balance. The goal is to find the balance between bias and variance, that is the optimal balance. This involves selecting an appropriate model complexity that allows a model to capture the underlying pattern. So there are a lot of patterns will be available inside the thing, but you have to capture the one of the best matching pattern without being overly sensitive to that noise. So noise here refers to the high level of data. So now come one example. Imagine trying to fit a curve to a set of data points. So when you come to the curve, when there is a curve is there, you have to understand how this curve. So I can show that before going to the curve, you have to understand how it is underfitting. A straight line, when you come to the graph, there it represents a straight line, might be too simple and systematically miss the curve. And the second category is overfitting, and third category is optimal balance, that just we have seen. But in terms of curve, a curve with a moderate level of complexity that captures the general trend of the data without being overly affected the noise in the best fit, that is. So there is a best fit will be there, noise will be there. In between that, we have to maintain an optimal balance, that is the optimal balance. When you go for high variance, very ugly wiggly curve that perfectly passes through all the points including noise, might not generalize well to the new point. So this will not match with the new data, that is the concept. Now how will you manage? How can you manage the trade-off? That is one type of question arises. So if you want to manage the trade-off, you have to go to the category called as regularization. So which means that adding penalties to the model complexity to prevent overfitting. So for any types of mismatch, you have to add penalty to the model. So adding penalties to model complexity to prevent overfitting. So this is not the underfitting, this is the overfitting. Now comes to the cross validation. Another term comes under the trade-off. Evaluating model performance on simple subsets of the data to get a more reliable estimate of its generalization ability. This is one of the category comes under the cross validation. That meaning is evaluating the model performance. Next one is ensemble methods, that is combining the multiple models to reduce the variance and improve overall performance. So if you want to get the overall improvements, you have to combine the various types of model, that is multiple models. And also feature selection or engineering and collecting more data. These are all some characteristics coming under the trade-off, managing the trade-off. So in essence, the bias variance trade-off is a fundamental concept. You have to understand what is a fundamental concept that guides the model selection and tuning process. Tuning process. So this model selection and tuning process will be happening in the machine learning, which helps to build a model that perform well on both the training data and unseen data. So we have to remember the two types of data. One is training data, another one is unseen data. So at last, the bias variance trade-off is a central problem in supervised learning. So there, you know that supervised learning is there, unsupervised learning is there. This types of the problem comes under the supervised learning, and you have to choose the model, but also generalizes well to unseen data. So maximum it deals with the unseen data. Unfortunately, it is typically impossible to do both simultaneously. High variance learning methods may be able to represent their training set well, but are at risk of overfitting to noisy or unrepresentative training data. So you have to go for the unrepresentative training data when it comes to the bias variance trade-off. So this is the graph. If you take the graph, this is the question: do you have ground truth data? If yes, if it is yes, how much? Okay, how much it is the truth about the data? Then if it is a large set and small data set, it goes for COT and reasoning help. If reasoning help is needed, you have to go for RFT. If there is not needed, you have to go for SFT. And if the truth of the data is false, that is no, you have to, the question is very simple: is the task verifiable? If yes, you have to go for same RFT. If that is no, you have to go for RLHF process. So this is one type of algorithm comes under the machine learning. So you have to keep remember how the flow chart is coming under with. So this is the next thing. If you take the data, training data and test data, this is unknown data. If training data have the error, how much error it will have, then it is low or high. And it is training data, again this ask the question of high and low. This, if it is high, you go for bias. If it is high, you go for variance in case of test data. Okay, so in case of training data, you have to say it as bias. In case of test data, you have to go say it as variance. Now this is another picture. So this is another picture, that is one is low variance, high bias, high variance. So if you match this combination, low bias and low variance, go for this types of error will be happening. And low bias and high variance, it will cost like this. And the combination of high bias and low variance, it will come like this. And the combination of high bias and low variance, it will come like this. So this is the best picture of the bias and variance trade-off. This shows the every complexity underlying with these models. So same category. So we seen the first graph. The same graph is coming here. This is error and this is bias variance error, and you have to go for x-axis and y-axis. Center one line will come. So this is the previous picture we seen how it is happening. So this is the graph representation. High bias will be graphically, it will be represented like this. Low variance will be graphically represented like this. This median will be there. High variance will be represented like this type of graph, median. So this is the same thing, high bias and low bias, which is shown actually in the previous picture itself. So now you come this small picture diagram. Low bias and high variance will be marked like this line. So optimal bias and variance will be marked as a curve. When high bias and low variance occurs, it will become like the unspecified shape. So this is the one of the graphical representation coming under the bias variance trade-off. So some technologies are related to the bias variance trade-off is there, that is combining multiple models to reduce variance and improve the overall predictive performance. And also you can say regularization and then cross validation. These are some technologies related to the bias variance trade-off. So most important bias variance trade-off use cases, some use cases are there. One is used in the bias in the financial forecasting, that is accurate prediction for stock market and prices. These are all coming under this category. And then comes to the medical diagnostics and customer behavior analysis and NLP, natural language processing. These are some various test cases coming under the various bias variance trade-off use case. Suppose if there is a small question come under the bias variance trade-off, this is a small question. Which of the following substantially more harmful to the test error than the training error? You have to answer. There are 4 options there. You can answer that it is easily, you can identify that it's a variance, because the reason is it is the error that you get when you run the trained model data back on the training data. Another small question. Which of the following learning class algorithm will be return a classifier if the training data is not linear separable? The answer is B, soft margin SVM. This is a perfect answer. The reason is mentioned here, due to the noise. And this is one more question. Modeling a class rule directly from the input data, like in logistic regression, fits which of the following classification methods? The answer is discriminative classification, because the reason is it learned the features in the input data that are most useful to the distinguish between the various possible classes. So it's a small question. What does bias in the variance state of represent? What actually it represents means it represents the error between the average model and ground truth. This is a perfect answer. Actually, what till now I explained, this is the reason. It represents the error between the average model. So, what does variance, the bias in this bias variance? What does variance alone represent? That is the thing is average variability in the model prediction for the given data set. It's a small question. You have to keep remember. This is the answer. And last one, bias variance trade-off in machine learning. Which of the following best describes? The answer is decreasing model complexity reduces variance but increases the bias. Okay, variance will be reduced. That is the main answer for this question. Okay, so this is the bias variance trade-off explanation. We can continue with the next session. Okay.